Hello students, in this video we'll discuss the eigenvalues of rotations, reflections, and projections in two-dimensional space. Let's first consider rotations in two-dimensional space. And so these matrices have the form cosine theta, negative sine theta, cosine theta, like so. So if we want to find the eigenvalues, we look at this equation over here, determinant of cosine theta minus lambda, negative sine theta, and then sine theta, and then cosine theta minus lambda is equal to 0. And so this equation over here, the characteristic equation, becomes cosine of theta minus lambda quantity squared is, let's say I'm going to have a positive sign, so that's going to put it together, so that's going to be negative sine squared theta. And so therefore your eigenvalues are cosine theta plus or minus I sine theta, which by Euler's formula is e to the I theta with a plus or minus, right? So for rotations, we have two complex eigenvalues. So two complex eigenvalues. Okay, and furthermore, we can sort of see that analytically because what happens is I know there can't be any invariant two-dimensional subspaces by rotation, right? This is my x and this is my y. And if I give you any subspace, let's say here's a subspace that's generated by v, so that's the span of v. Then if I rotate by theta, then rotation by theta is going to move me right over here, right? Onto this subspace. That's theta over there. And if we call this r theta, then this subspace is going to be r theta of the span of v, and therefore there are no invariant subspaces, no one-dimensional invariant subspaces. Okay, great. So that takes care of rotations. Now, of course, in other words, there are eigenvalues, but they're complex eigenvalues. And so what we have to do when we're doing diagonalization procedures, we have to put these into a different bucket than the ordinary real value diagonalization. All right, let's talk about reflections next. Reflections. Okay. And so if we want to reflect over the line, reflection over the line, y equals ax. We proved in the previous video this is 1 over 1 plus a squared. And then a squared minus 1 minus a squared, 2a, and then a squared minus 1. And so that's what the matrix is over here. And so I claim that we can sort of geometrically visualize what the invariant subspaces are, right? So if we look at this over here, so if we look at the two-dimensional space, here's x and here's y. And then if I have the line of reflection, so this is my line of reflection over here, if that's y equals ax, then I know that if I reflect over the reflection axis, nothing happens, right? So if I give you a point on the reflection axis over there and say reflect over the reflection axis, you just stay on the reflection axis. So I know that the reflection axis itself is an invariant subspace. So this line over here, which I can represent as 1a, should be an invariant subspace, right? Invariant subspace. Okay, so let's verify that. So let's plug that in to our matrix and see what we get. So if I plug in, I have a 1 over 1 plus a squared, and then a 1 minus a squared 2a, and then a 2a squared minus 1. I'm going to plug in a 1 for x, and then an a over there like that. That's my vector I'm plugging in. So I'm testing to see if this is an eigenvector. This is 1 over 1 plus a squared. And then what do I get? I get a 1 minus a squared plus 2a squared. And then down here I get a 2a, and then a cubed minus a cubed minus a. So this is a 1 over 1 plus a squared. And what's on top over here, what's on top is a squared plus 1. And what's on the bottom over here, it's going to be a cubed plus a. So that's going to be an a times a squared plus 1, right? Excellent. So the a squared plus 1's cancel out. And this is just equal to 1a, okay? What have we just shown over here? If I call this reflection matrix over here RA, I've just shown that RA of 1a is equal to 1a, and that says that 1a is an eigenvector of the reflection matrix with eigenvalue 1, right? So in other words, I can sort of say that this is really, so RA 1a is 1 times 1a. Beautiful. Now, I want to find another invariant subspace of this reflection matrix, and of course, geometry comes and helps us here. If I wanted to find another thing I could do, if I look at a line that's perpendicular to this line over here, like that, and of course, how do I find perpendicular lines? That's y is equal to negative x over a, the negative reciprocal slope over there. I know that if I reflect perpendicularly, this point over here will go to this point over here, so it looks like it's going to go in the opposite direction. So I claim that this perpendicular slope is also going to be an invariant subspace. And so how can I check that over there? Well, I can pick a point. If I pick x equals a, then y is equal to negative 1. So now let's consider the calculation 1 plus a squared, 1 minus a squared, 2a, a squared minus 1 on the perpendicular line segment. So I'm going to look at this invariant subspace. I'm going to look at x equals a, y equals negative 1. So let's see what we get. We get 1 over 1 plus a squared. And then we're going to have a what? We're going to have a minus a cubed. So we have an a minus a cubed. And then minus 2a. And then down here we'll have an a squared. And then a negative a squared plus 1. And so what will the top be? The top is going to be this, 1 plus a squared. And then we're going to have a everything is negative. It's going to be I'll have a negative a, and then a squared plus 1. And then down over here, I'm just going to have an a squared plus 1. So what happens now is this becomes negative a, 1 when I divide through. And that's not the starting vector. That's not a negative 1. That is the opposite direction. So this is going to be negative a negative 1. And therefore, we see that Ra of a negative 1 is negative 1. So I have two eigenvalues of this reflection, right? The eigenvalues, lambda is going to be plus minus 1. And your eigenvectors are going to be a1 and, a negative 1 and 1a, those perpendicular directions. Now, finally, let's go to projection. So the last case to deal with is projection. So for projections, your matrix PA, I'm going to reflect over the same line, y equals ax, is going to have almost the same form because there's clearly a relationship between projections and reflections, right? And this time you're going to get a 1, an a, and an a squared, okay? It's important to note, too, that these matrices over here are symmetric matrices, okay? Now, if I'm going to project onto this line over here, if I project onto the line y equals ax itself, nothing should happen, so I expect the same thing to happen over here. So let's consider PA applied to 1 and then a. So 1a will be 1 over 1 plus a squared. And then 1a squared. 1a is going to give me what? Is going to give me 1 over 1 plus a squared. 1 plus a squared. And then a plus a cubed. Which we see is exactly just by canceling out one of the a's, this is the same thing as just 1a. So if you start on the axis of projection, what will happen? If you start on the axis of projection, you will remain on the axis of projection, okay? And then similarly, what happens if I plug in the perpendicular direction to the projection? If I look at PA of what? PA of a negative 1 will be 1 over 1 plus a squared, and then 1a squared applied to a negative 1. What we're going to see over here is what? We're going to see that I'm going to have an a minus a, that's going to give me a 0, and then a squared minus a squared, that gives me a 0. And so that says that P has null space, which is the span of what vector? The span of the vector a negative 1 is a one-dimensional span. That makes perfect sense too, because where am I going to project everything? I'm going to project everything right where? If I'm on the line perpendicular, I'm going to project right onto the origin. And when you project onto the origin, that corresponds to finding points in the null space of the projection matrix over here. So in each of these cases, we see in the classical geometric cases, we have eigenvalues which are complex for rotations. We have eigenvalues, and then we have eigenvectors, which are, if you're doing reflection over a line or projection onto a line, the eigenvectors are going to be the line itself of projection. and the line that's perpendicular to that line of projection. That also comes from a more general fact about symmetric matrices, that the eigenvectors of symmetric matrices are going to be, real symmetric matrices are going to be perpendicular to each other. We see that exactly here. The fact that they're perpendicular to each other. Thank you very much.